It is November 1883, somewhere beneath the cobblestones of Holborn, in the cold, wet clay that sits 40 feet below the city's noise and smoke and horse traffic. A crew of navvies is pressing the last section of cast iron pipe into place.
All right,
They
together
don't
now.
fully understand what they're
Push!
building. Nobody does yet. They just know the pipes are heavy, the tunnels are dark, and the pressure the engineers keep talking about, 700 pounds per square inch, is enough to punch through solid brick like a rifle shot. They seal the joint. They step back. Someone up the line opens a valve. Nothing explodes. Nothing fails. The water moves Dot, and for the next 94 years, it never stops. London in the 1880s is a city trying to eat itself alive with its own ambition. There are now 4 million people packed into a radius that, just a generation before, had held barely 1 million. The docks are roaring. The banks are towering. The theaters, the hotels, the warehouses, the newspaper printing houses, all of them hungry for the same thing: power. Mechanical, reliable, instantaneous power. Not the steam power of individual boilers, each one requiring its own coal, its own stoker, its own chance of catastrophic explosion in a basement under a crowded building. Something cleaner, something central, something that could be switched on the way you'd turn a tap. Edward Basand Ellington had been thinking about this problem for years. He wasn't a famous man. He wasn't the kind of Victorian engineer who ended up with a statue in a park or a bridge named after him. He was methodical, precise, slightly obsessive, and he had developed a particular fascination with something that most engineers of his era treated as a curiosity: hydraulic power. The principle was ancient. Water under pressure can do mechanical work. Push it through a small pipe fast enough, and it becomes a tool. It can lift, compress, rotate, shove. The Romans knew this. The millwrights knew this. But nobody had ever seriously proposed piping it under an entire city. Ellington proposed it. His idea was staggeringly simple at its core. Build a central pumping station. Fill it with the most powerful steam-driven pumps that Victorian engineering could produce. Draw water from the Thames or the municipal mains. Pressurize it to 700 PSI, roughly 48 times the pressure inside a standard boiler of the day. Then run pipes out under the streets like a circulatory system, like the veins of the city itself, and let anyone who wanted to use that pressure simply connect to the network. Pay a quarterly rate. Get mechanical power on demand, 24 hours a day, without a boiler, without a stoker, without coal deliveries, without the constant low-level fear that today is the day the basement explodes. When he presented the concept to investors, some of them laughed. He went ahead anyway. The London Hydraulic Power Company received its parliamentary authorization in 1871. It took another 12 years to actually open for business, which tells you something about the scale of what they were attempting. The pipes alone were a manufacturing challenge that had no real precedent. Cast iron, thick-walled, each section tested individually before it went into the ground. The joints had to hold under sustained pressure that most industrial equipment of the era would struggle to reach, let alone maintain indefinitely. The tunnels and ducts under London's streets were already a negotiation nightmare. Gas mains, sewer lines, the early underground railway, the telegraph cables, the water mains, all of them already crammed into the Victorian underworld. Finding routes for the hydraulic pipes required not just engineering skill, but a particular kind of spatial diplomacy. A constant 3D chess game played in the dark. The pumping stations were another thing entirely. Ellington built 5 of them across central London, at Grosvenor Road in Pimlico, at City Road in Islington, at Wapping on the riverfront, at Falcon Wharf in Southwark, and at Bankside. Each one was a cathedral of Victorian industrial machinery. Massive beam engines at first, then later triple expansion steam engines of breathtaking precision, all of them driving pump cylinders that could push water through the network continuously. The engines were monitored around the clock. Pressure gauges lined the walls like clocks in a watchmaker's shop. The stokers fed the boilers in measured rhythms. The engineers walked their rounds through the night, listening, because that's what you did with 700 PSI in a cast iron network under a city of 4 million people. You listened. Any crack, any joint failure, any unexpected pressure drop. These were not abstract engineering problems. A catastrophic failure under a crowded Victorian street could kill people, collapse buildings, turn a thoroughfare into an instant flood zone. The men who ran the pumping stations took that responsibility not as a concept, but as a physical weight they carried every shift. The pipes never cracked. The joints never failed, but we're getting ahead of ourselves. The first customers were exactly who you'd expect from 1883. The docks, the newspaper printing houses. The hydraulic power company's pipes ran right through the heart of London's commercial infrastructure. And the businesses that connected to the network in those early years shared a common profile. They needed a lot of mechanical force. They needed it reliably. And they had already grown tired of the coal and boiler. Solution: cranes. That's where the system earned its first serious reputation. Before hydraulic power, loading and unloading ships in London's docks was a human and animal operation. Men and horses, ropes and pulleys, the same fundamental mechanics that had moved cargo since the Bronze Age. The steam crane had improved things. But steam cranes were slow to heat, required constant attention, and each one was essentially its own small factory. Hydraulic cranes were different. A dock worker could connect a crane to the city's hydraulic main, operate it at full power within seconds, and when the job was done, close the valve and walk away. No cool down, no wasted fuel, no boiler to maintain. The docks adopted the technology with the enthusiasm of men who had been spending a decade waiting for exactly this thing. Then the lifts began. The 1880s were London's first serious skyscraper moment, not by modern standards, but by the standards of a city that had spent most of its history building in brick to 4 or 5 stories. The new commercial buildings along the Strand, around Piccadilly, in the financial district of the city, they were climbing to 8 stories, 10 stories. Heights that made staircases genuinely impractical for the movement of goods and increasingly unpopular for the movement of people. Hydraulic lifts had existed since the 1840s, but they needed their own pumping equipment in the building's basement. Once the London hydraulic power network started threading its pipes under those streets, the equation changed. You could install a lift in a new building, connect it to the city's mains, and never worry about a pump room again. By the 1890s, hundreds of buildings in central London were running lifts off the network. Hotels, department stores, the new generation of office buildings that were turning the city into something recognizable as a modern financial district. There were hydraulic presses in the printing works that produced London's newspapers, the same technology, running at pressure, that stamped the news into paper at speeds that would have seemed magical to the generation just before. There were hydraulic riveters, hydraulic jacks, hydraulic cranes in the West India, docks in the Surrey Docks and St. Catherine's alongside the Tower of London. The Tower Bridge itself, that improbable, glorious Victorian confection of Gothic towers and engineering bravado, opened in 1894, used hydraulic power to raise and lower its bascules. 6 million pounds of steel and granite, lifted by the pressure of water and pipes that ran under the streets. The engineers who built the bridge connected it to the London Hydraulic Power Company's network, as a matter of course, the same way a modern building connects to the electrical grid. That's what the network had become by the turn of the century. Infrastructure. Not a novelty, not an experiment, but a fundamental layer of how London functioned, as assumed and invisible as the gas, mains, or the sewers. The 20th century arrived with electricity. This is the part of the story where you might expect the London Hydraulic Power Company to see the writing on the wall and begin its long decline. And in a way, that's exactly what happened, just much more slowly than anyone predicted. And for reasons that say something interesting about the gap between what a new technology can do and what it immediately replaces. Electricity was superior. Nobody seriously contested this. Electric motors were more flexible, more easily scaled, more easily controlled than hydraulic machinery. The generating stations going up along the Thames in the Edwardian years were building toward a grid that would eventually power the entire city. In the long run, the hydraulic network was obsolete from the moment electric power became viable. But in the short run, and in London, the short run turned out to last 60 years. Hydraulic power had two advantages that electricity couldn't easily match. The first was its existing customer base. Hundreds of buildings already had hydraulic machinery installed. Replacing working equipment with electric alternatives cost money and time. And as long as the hydraulic power company kept its rates reasonable, the economic case for switching was rarely compelling. The second advantage was more fundamental. Hydraulic power, unlike the early electrical supply, was safe in environments where sparks and ignition were dangerous. Warehouses storing cotton or grain, buildings where gas was present, environments where an electrical fault meant fire or explosion. In these places, hydraulic power remained the rational choice well into an era where electricity had otherwise won the argument. So the network adapted, contracted slowly, and kept running. The pumping stations modernized. The great Victorian beam engines were retired as more efficient equipment became available. Electric motors eventually replaced the steam engines at some of the stations. The company using the new technology it was ostensibly competing against to power the system that predated it. The pipes under the streets aged but held, decade after decade. That cast iron network laid down by Ellington's crews surviving 2 world wars and every other disruption the 20th century could throw at it. During the Blitz, the pumping stations kept running. Through nights when the sky above London was orange with fire, and the streets above the pipes were buried under rubble and shattered glass, the pressure in the mains held steady. It's not a dramatic story. Nobody writes poems about water pressure in cast iron pipes during wartime. But somewhere in that fact, there's a particular kind of Victorian stubbornness that feels worth honoring. The thing was built to work. It worked. By the 1960s, the customer list had shrunk considerably. The great dock system that had been the network's original core market was in its final decline. Containerization was coming, and with it, the slow death of London's traditional waterfront economy. Many of the old hydraulic lifts had been replaced with electric models during post-war renovations. The printing houses had modernized. Building by building, decade by decade, the connections to the network closed. In 1977, the London Hydraulic Power Company shut down. It was not a dramatic ending. No ceremony, no final catastrophic failure, no moment of sudden obsolescence. The last pumping station simply stopped. The pressure in the pipes dropped for the last time. The water that had been moving through that cast iron network continuously for 94 years went still 0.150 miles of pipe, 700 PSI of sustained pressure. 94 years. No leaks. The engineers who decommissioned the system reportedly found the pipes in better condition than expected. The cast iron had held. The joints had held. Whatever Ellington's crews had pressed into place under Holborn in 1883 had simply refused, across 9 decades, to break down. Here's what we sometimes get wrong about Victorian engineering. We look at the scale of what they built, and we imagine a kind of reckless confidence. Men who didn't know enough to know what could go wrong, who built big because they didn't understand the risks. But that's exactly backwards. The engineers who designed the London hydraulic power network understood what 700 PSI of sustained pressure could do to a joint that failed, to a pipe that cracked, to a street above a catastrophic rupture. They designed for it. They tested for it. They built in redundancy. The 5 pumping stations weren't just geographic distribution. They were backup capability. If one station failed, the others could maintain pressure in the network. The system was resilient, not because its builders were optimistic, but because they were afraid. That fear produced something that lasted almost a century. There's a conversation worth having about what it means to build infrastructure in a city. London's hydraulic network is, in some ways, an argument against the way we think about technology now. The assumption that the new thing will always and quickly replace the old thing. That obsolescence is sudden. That the world reorganizes itself to match the latest innovation. The hydraulic network became obsolete by any reasonable engineering standard before World War I, and then it ran for another 60 years because the real city, the physical city, with its installed equipment and its economic calculations and its simple inertia, takes its own time. The pipes are still there, some of them anyway. A section of the network was repurposed in the 1990s by a company called CityLink Telecommunications, which ran fiber optic cables through the old cast iron conduits rather than digging up London streets again. The infrastructure that Ellington built to carry water at pressure now carries light at the speed of information. The city changed everything it ran through those pipes. The pipes themselves survived. Edward Basant Ellington died in 1894, the same year Tower Bridge opened using his network. He lived long enough to see his system become essential, to watch the cranes working in the docks and the lifts rising in the new hotels and the bascules of that great, improbable bridge lifting on the pressure he had spent his career making real. He didn't live to see the network run for 94 years. He didn't live to see electricity nearly kill it. And then the city's sheer physical stubbornness keep it alive anyway. But he built the thing. He built it well enough that it ran, without a single catastrophic failure for nearly a century. In a city that was simultaneously tearing itself apart and remaking itself. In 2 world wars and the social upheavals of the 20th century and all the technological revolutions that made his invention seem ancient. The pipes held. There's something in that worth sitting with. We live in a moment that tends to celebrate the new thing, the disruptive thing, the thing that makes the old thing obsolete. And that's not wrong. Innovation matters, and the hydraulic network was genuinely replaced by better technology. But there's another kind of achievement that gets less attention. The thing that is built so well, with such care and such fear and such precise engineering, that it simply outlasts its own obsolescence. 150 miles. 700 PSI, 94 years. No leaks. Somewhere under London, the cast iron is still there. It's not carrying anything anymore. Just waiting, the way all good engineering waits, patiently, without complaint, holding the shape it was given by the people who decided in 1883 that if you were going to do something, you were going to do it right.